Yes, thank you for the introduction, Martin, and hello to everyone who's joining for this presentation today. Today I will talk about a large-scale vibroacoustic measurement campaign and the subsequent analysis performed utilizing STI at our department. And this presentation is split up in these two topics, so measurement campaign and analysis. And the measurement part is a combination of publications of my colleague, Dr. Winter, which he held at two conferences this year. And he will also be answering questions related to measurement you might have later. So first of all, I want to start with a little motivation. Passengers in aircraft cabins are impacted by a lot of noise from different sources. First, we have the turbulent boundary layer, which is acting on the outside of the fuselage. And this boundary layer excites the fuselage and eventually also the cavity inside the cabin, which results in noise. But also we have engines and subsystems installed in and on the aircraft. And these systems transmit noise over the air into the cabin, but also these systems introduce or induce vibrations in the overall structure, which eventually also result in noise due to fuselage vibrations. And one of the more prominent transfer paths is between the engine and the fuselage. And this is also one of the focuses of this presentation. The test campaign, which I will talk about in this chapter, is part of a currently running project. And I will give a short overview before covering the actual measurement campaign. The project we are currently working on is called DA9 Engine Tonal Noise. And the main focus of this project is the development of methods for cabin noise prediction and the reduction with regards to engine tonal noise. The kickoff of this project was in October 2021. And the first task, and one of the main tasks in this project, was the large-scale ground vibration test performed in March of this year. And as you might realize, this is a very short time window to plan and perform such a campaign, considering that the aircraft still needs to fly afterwards and under no circumstances can be damaged. So I have to say this was a great collaboration of different groups of our department and also other DLR institutes. Further task which will follow from now on in this project is the correlation and updating of an FEI finite element model of the ISTAR, and also the further implementation and experimental validation of active cabin noise reduction systems. This project is within the framework of Clean Sky 2, and as a cooperation partner, we had the manufacturer of this aircraft, which is Dassault Aviation. So some facts about the aircraft we worked on. The DLR ISTAR. ISTAR is an acronym for In-Flight Systems and Technology Airborne Research. This aircraft is in service at the DLR since 2020. And it is a Dassault Falcon 2000 LX. But I have to say that the ISTAR is no usual aircraft. It's a research platform. And with this, it comes that this aircraft is heavily upgraded with 62 acceleration sensors and also numerous strain gauges throughout the structure. And in the near future, the aircraft will also be modified with a novel flight test control system, which will improve the capabilities as a research platform even more. Here on the right side, you can see a mock-up of the ISTAR, and the vectors you can see, which are plotted in the mock-up, indicate the locations of the permanently installed acceleration sensors. And as you can see, most of the sensors are placed in the wings and also the vertical and horizontal tail plane, because these sensors are mainly installed for structural health reasons, and thus they are not suitable for vibroacoustic measurements, because they can't capture the vibroacoustic behavior of the fuselage, which is here very interesting. So for our measurement campaign, we had some requirements in order to do the measurement. First, we wanted to do experimental model analysis afterwards. And for this reason, we needed to excite the aircraft with electrodynamic shakers. But additionally, we also wanted to do an engine excitation to capture the realistic structural behavior of the fuselage. This came with time constraints, as the engines can only run for so long on the fuel which is tanked, and also considering the costs of the fuel for such an engine run on ground. Additionally, we wanted to have a pretty good sensor density on the fuselage in order to estimate structural intensity from the measurement data. The requirements, and on the opposite we had the limitations which were given to us. There was only 2 weeks of time for testing for this whole measurement campaign, and as I already mentioned, the limited engine excitation time. And also we had 300 acceleration sensors available to measure the most or as much as possible of the vibroacoustic behavior of the aircraft as possible. In order to perform the measurement under the given limitations, we decided to use a rowing sensor grid. This rowing sensor grid method was developed during previous vibroacoustic tests on a A400M fuselage and an A320 fuselage demonstrator. And just to give a short wrap up, this rowing sensor grid, it basically allows to perform measurements with a dense grid on the full fuselage or on fuselages, but with only a subset of sensors available. The challenge with this method are the uncertainties introduced into the measurement by performing the same excitations repeatedly. So considering the requirements and limitations I just talked about, we designed the measurement grid, which you can see here on the right. We identified 1,310 sensor positions to be measured, and in total we designed 5 half-ring configurations. So you see the full measurement grid, or all the measurement positions we measured on the aircraft here in this grid, but the yellow marked ones here are the first configurations of sensors, so a subset of the full measurement grid. For every consecutive configuration, the installed sensors here marked in yellow were pushed one step back further towards the tail of the aircraft until every sensor position was measured. And for every sensor configuration, we also use the same excitation locations, which I will cover in a few seconds. To the main measurement positions, we also had 24 fixed sensors installed on the offside of the aircraft. And these sensors acted as a validation set, as the aircraft is not fully symmetric, but were also used to estimate the uncertainty of the rowing grid measurement. Here you can now see the 4 excitation locations we used during the measurement campaign. For every sensor configuration, we excited the structure with a random excitation up to 400 Hertz at these 4 excitation locations. 2 of them are located before the rear pressure bulkhead and 2 in front of it. So the rear pressure bulkhead is the end part of the pressure capsule in an aircraft, so which is pressurized during flight. and it is located about in this location in front of the engine attachment to the fuselage. And yeah, we chose 2 excitation points behind the rear pressure bulkhead on the fuselage itself, which this vector indicates, and also 1 excitation on the pylon of the engine, which is this vertical one, in order to mimic the engine vibrations which would occur due to the engines running. And the other 2 excitation points is the one in horizontal direction here and this vertical one, and these are placed in front of the rear pressure bulkhead. And we chose these in order to have higher amplitudes in the main fuselage to do modal analysis and model updating with these measurement data after the measurement campaign. So 1 second. But we didn't only measure the full aircraft with shaker excitation, but as I already mentioned, we also used engine excitation. And for the engine excitation measurement, we used a subset of sensor locations to measure. So we pushed all the available sensors we had to the back of the aircraft, closely focused around the pylon to capture the vibrations while the engines were running in this location. Yeah, but for this part of the measurement campaign, we had very strict guidelines because we couldn't use a rowing grid because it was not possible due to time constraints because the engines couldn't run so long. But also we had to tape down every single sensor and the cables to the fuselage to make sure that no sensor or cable would suck into the engine, because this would have been catastrophic. Yeah, so much to the measurement setup. Now to give you a better idea of how such a large-scale measurement campaign looks, I will play the following video we created of this campaign. It will provide an insight in the work of these 2 weeks compressed into 2 minutes. The video will be played without music, so I can comment on the tasks, but at the end you will hear the engine sound, so depending on your speaker volume it could be loud, so be advised. In the beginning we had to mark every single sensor position. This took us about 2.5 or 3 days. And we weren't able to estimate the positions of the stickers by measuring, but we had to identify the rivet crossings on the surface of the aircraft. After marking every sensor position, we installed the first configuration of sensors and performed the excitations with the shaker on the 4 locations I showed you earlier. Here you can see first results, and yeah, after every excitation round we pushed the sensors 1 step back towards the tail of the aircraft and performed the same excitations with the shaker again. This is the excitation on the top of the aircraft. And here you can see the full results for the full fuselage. After the configurations 1 to 5, we pushed the sensors back to the tail of the plane in order to prepare for the engine runs, and we had to tape everything down, all cables and also the patch panels, in order that the aircraft can roll out onto the apron where the engine tests were performed. We set up our measurement equipment there, and yeah, then the engines were turned on. The engine runs, for the engine runs, we also had a specific schedule. The engines were running at different percentage stages. So the engines were running at 20, 50, and 80% of the maximum performance level. And we also let the engines run both at the same time, but also individually on the left and right side to capture the vibrations in the fuselage. Okay, so much to the measurement campaign. Now I will talk a little bit about the data quality and the results we acquired as a measurement data. Here you can see the standard deviation of the fixed sensors on the offside of the aircraft for all sets of configurations of the rowing grid. The amplitudes deviation over the whole frequency range is about 20%. And at the bottom you see the phase plot, and over the whole frequency range, the deviation of the phases is about 7%. This may look bad on first sight, but it is to mention that our post-processing is heavily focused on performing model analysis, while model analysis, which relies on having the best possible phase information, which, as you can see, is present. Also, model analysis is usually performed up to 100 or 150 hertz, for which the amplitudes, as you can see on the top, is still very good, because the largest deviations, especially in the amplitudes, start to increase from about 200 hertz. And yeah, for this measurement quality, we were able to create these beautiful operational deflection shapes. Here's an example for the full fuselage deflection shape at 74 hertz for the vibro-acoustic test. From the excitation point, which is here where the highest amplitudes are present, the deflection shape propagates through the whole structure. And if you have a close look, you can also see that at this location where the rear pressure bulkhead is approximately located, is that the resulting amplitudes in the back of the airplane are much smaller than in the front. As a comparison, here you can see the operational deflection shape also at 74 hertz, but for the engine excitation. And yeah, as for the engine excitation, we only had a subset of sensors, only in the back of the aircraft. We only see the deflection shape in high quality at the back, and only some, my screen turned black. Can you still see the presentation?
Yes, all good.
Okay, all right. Yeah, and we had some single sensors installed in the front just to capture the most important deflection shapes. Yeah, the plan with this data is to apply the measurement data of the engine run onto an FEM model of the ISTAR, which will be updated in order to estimate the full structural behavior during the engine run. However, this model is not ready yet, so currently we use a workaround. Here I have the picture again for the sensors all located at the back of the aircraft. Yeah, currently we have a workaround. From sensors we installed on the pylon during the engine run, we were able to extract the engine tonal frequencies. And yeah, we use these frequencies to identify the operational deflection shapes from the shaker excitation on the pylon in order to visualize how the fuselage vibrations might look for the engine excitation on the full fuselage. So you can see here that frequency 1, 2, and 3 are shown. And the higher the frequencies get, the more local the vibrations seem to be. But it's also interesting to see here that for the frequency 2, that the amplitudes in the front of the main fuselage are much smaller than for F1 and F3. which indicates that the rear pressure bulkhead, especially for frequency 2, is a pretty strong barrier for the vibrations happening in the back. Yeah, so much for the measurement campaign. Now we'll talk about the analysis we performed on this measurement data. And in our department, the structural intensity is developed for some years now to investigate transfer path. And as the structural intensity is not commonly known, I will give a short introduction before showing the results we generated by applying this method. The fundamental idea of the structural intensity is to calculate the vector quantity indicating the wave power per area flowing in a certain direction. And most people are familiar with the similar sound power intensity. The sound power intensity indicates the power per area and the direction of the sound propagating through space. And in order to calculate the sound power intensity, it is necessary to measure the scalar pressure value in a certain position and also have the velocity vector available. But in the case of the structural intensity, we not only use a simple scalar pressure value, but the full tension tensor here for an example for a material cube in 3D space. So we have 9 tension values we need to incorporate into the calculation for the structural intensity for a full material block. As an example how these structural intensity fields look, here is an example of a simple plate which is fixed at the edges, and a simple point force excites the structure, which is here the source of power flowing into the structure. And we also have a local dissipation sink, which is a dashboard damper here. And you can see how between source and sink, there are transfer paths evolving where the energy flows from the excitation point into the local dissipation. But we not only can calculate these structural intensity fields for simple plates, but it's also possible to do for much more complex structures like this generic passenger aircraft wing box. And as you might realize, these two examples use shell elements in comparison to the material block I just showed here on the left side for the equation. And yeah, this is also this is where the SDI gets tricky, because while you can calculate the SDI for continuous 3D structures in the FEM, where you get all the necessary results from the measurements from the mesh you generated, this is not possible for the SDI estimation from measurement data. Because when measuring structures, it is most of the time only possible to access the behavior of the surface, but not the inside of these structures. So usually to estimate structural intensity, it is common to use shell elements, because here the measurement from the surface of the structure gives you enough information to estimate the structural intensity. And here you see the equation I showed you on the previous slide, but adapted for shell elements. And you also see here that we use the forces and not the tensions. So this results in the power flow and not the intensity anymore. However, now that we use shell elements, we can assume thin-walled structures, so the Z component of the power flow can be neglected. And with the measurement values, we can access from measurement campaigns, mostly in Z direction, so in the normal direction of a surface, we can calculate the power flow. It is also possible to measure the X and Y directions of a surface, but only with measurement systems which are capable of this, like 3D laser vibrometry or the digital image correlation technique. So in the end, we end up with these blue indicated values, which we need to estimate in order to calculate the power flow in structures, because we have only given the green measurement values. So the process we use looks as follows. First of all, we measure the velocity field in Z direction, or if possible, also in X and Y direction. After that, we connect these measurement points to an element mesh, for which we also choose shape functions. So basically, we build up the geometry of an FEM mesh. After that, we can approximate rotational degrees of freedom around or about X and Y direction with this element mesh and the respective shape functions, and can also estimate the element strains and with the material, with some material properties, also estimate the necessary forces you saw in the equation before. And these 4 steps, number 2 to 5, are basically the FEM approach, which also a respective program uses in the background. After estimating all these data, we can finally calculate the structural intensity. And as I showed you before in the example structural intensity fields of the plate and the wing box, these power flows or structural intensity flows can become very complex and confusing, so you can't directly see where sources and sinks are present. And this is why there are also some post-processing techniques, and one of the most important is the so-called Hodge-Helmholtz decomposition, which is a mathematical construct and allows to decompose a vector field in 3 distinct vector fields, which help to identify certain features of a vector field. And while there are other post-processing steps, the Hodge-Helmholtz decomposition is very important, and this is why I want to explain this one also very shortly. So we have a complex vector field here on the left, and when you apply the Hodge-Helmholtz decomposition, you can decompose the field in the divergence field and the rotational field, and also actually a third component, which is here indicated by R. But basically, this third vector field is just there for mathematical completeness, because it's basically a constant offset of the vector field. But the 2 important ones, or more important ones, are the divergence field and the rotational field. And the divergence field will show you sinks and sources from your original vector field. And it also better allows to calculate detailed power balances between the singularities. So you, for an example, could do a path integral about around these 2 points and calculate how much power is flowing into your system and out of your system, and through the difference you can estimate how much power was dissipated throughout the structure between these 2 points. And the rotational part of the vector field is basically the energy which doesn't have a direct sink or source, but which is flowing continuously through your structure while vibrating. So now I can show you some results. On the top, you see the operational deflection shape for a certain frequency. The excitation is here where the vector is plotted, and on the bottom, you see the divergence field of the structural intensity after applying our method. You can see that from the excitation point, the power is flowing outwards from the point and into the structure. At this example, the energy mainly stays in the area of the excitation point, but also travels past the rear pressure bulkhead, which is probably located around here, into the back of the aircraft. But you can also see a slight transfer path building up in this region, because here are also still some yellow indicated vectors appearing. So this is a result for a shaker excitation of the fuselage. but we also wanted to see how the divergence fields look for the engine runs. So we used the operational deflection shapes at the engine tonal frequencies, which I showed you earlier. And the results for these 3 frequencies at the engine tonal frequencies look as follows. You can see that for all 3 frequencies, the vector fields look similar. So mainly the energy is flowing in this area just below the pylon. And yeah, what's interesting is that for all 3 frequencies, which are a little bit apart, the vector field looks similar, which indicates that the structure is very high or has a very high damping through the rivets which hold the structure together. Yeah, and as I said, the area below the pylon has a very distinct character. And the question is here, why does so much energy flow in this location as a sink? Is it maybe a good geometrical noise emitter, as this area of the back of the aircraft was very flat, almost like a plate? Or are there components installed inside which act as a mass tilger, something like this? Yeah. And to do a kind of a comparison between these fields, I had a look into it. Where are the differences? So in comparison to F2 and F3, at the frequency F1, there are also power flows appearing on the top of the pylon, which is not present in the other parts. And also here for F2, we did a more detailed transfer path analysis. So from the pylon attachment, which acts here as a source, the energy is input into the structure, and also high dissipation is happening here just below this red area. But when you look at the rest of the vector field, it is also apparent that a lot of vibrations travel from the front to the back and also flow. It seems like it flows in this frame of the aircraft. And as I already said earlier, the rear pressure bulkhead is located about in this area, and we also see a second kind of a source in this area. At the frequency F3, there is power flow missing at the very back of the aircraft, and also we see a kind of a second sink in the area of the rear pressure bulkhead here. Yeah, this is a first approach for transfer path analysis with the structural intensity in our department. And this brings me also to the end of the presentation, a short summary and outlook. So the measurement campaign was kicked off to start in 6 months. We did a successful test with good data quality, and data quality was sufficient enough to do STI analysis afterwards. And we did a first transfer path analysis based on the engine tonal excitations. We used the artificial excitation for that because we don't have the structural response for the full engine runs. And we identified a low dependency on the excitation frequency in the mid-frequency range because of the high structural damping of the aircraft. The outlook regarding this project is that we want to validate and update numerical models using the model analysis, and also do energy correlation to improve the model updating. We want to apply the engine vibrations we measured during the engine runs to numerical model and extend the results for the full fuselage. And of course, we want to do further detailed assessment of the power flows as soon as these models are available. Thank you for your attention.